yetkisi veriyorum. Record'u başlatırsınız hocam.
Okay. Now it's recording, yes? Right? Okay. Okay. Welcome, dear all, to the international symposium. The presentation will be focused on advanced material and nanotechnology, having an energy and storage and lighting objectives, biomedical topics. And the first presentations will be related effects of sintering time on density and microstructure, right? And will be presented by Seher İrem. Dear Seher, are you there?
Yes.
Okay. If you're ready, you can start, and I can give a share screen permission from here. Okay. I let you know. You can reach easily.
You can see?
Yes, very well, very clear. Okay. Yes.
Hello, it's Seher İrem Aydoğan, and this is the presentation of the study named Effects of Sintering Time on Density and Microstructure of Boron Carbide Particle Reinforced Aluminum, which contains 15% by weight silicon, 2.5% by weight copper, and 0.5% by weight magnesium composites in microwave sintering process. The topics mentioned in the presentation are the aim of this research work, experimental methods were followed, results and discussions, conclusion of the research work. This study aims to determination on the effects of sintering time on density, structure, and hardness of boron carbide reinforced hypereutectic aluminum silicon alloy composites produced by cold pressing and microwave sintering process. Composite materials have become a requirement for modern production technology due to the fact that composite materials have improved physical and mechanical properties. The main application areas of composite materials are the aerospace, military, and automobile industries. Different techniques are used for the production of metal matrix composites. The most common of these techniques is powder metallurgy, cold pressing, and sintering, one of the PM techniques. Different sintering techniques are used. One of these techniques is microwave sintering. Microwave heating is due to the material's ability to absorb high-frequency electromagnetic energy and convert it into heat. The microwave heating occurs from the core and generates heat inside the sample. The use of microwave energy for sintering materials has the advantages in reduced processing times and energy saving. Microwave sintering has been recognized as a time-saving and cost-effective process as compared to the conventional powder metallurgy processes for sintering composite materials. In this study, hypereutectic aluminum silicon alloy has been chosen as the matrix material. Boron carbide was used as a reinforced. Aluminum boron carbide composites were produced by cold pressing and microwave sintering techniques. The effects of sintering time on density, microstructure, and hardness was investigated. Table 1 represents the nominal chemical composition, the matrix material. The Alumix 231 powders with an average size of about 75 micrometer was produced by inert gas atomization. The reinforcement particle boron carbide has a density of 2.52 grains per centimeter cubes and average powder particle size is 10 micrometer. The production states shown in the table 2. Alumix and boron carbide powders were mixed in triaxial mixer. The mixture powders were pressed by applying 620 megapascal uniaxial pressure by cold pressing technique, and samples were sintered by microwave sintering technique. The samples were subjected to the elimination of the lubricant at 400 degrees for 20 minutes. Sintering was carried out at 555 degrees for 15, 30, 45, 60 and without holding time. Heating rates to lubricant elimination temperature was set at 5 degrees per minute and sintering temperature was set at 10 degrees per minute. Green density and sintered density of the samples were measured through the Archimedes technique. Optical microscope and scanning electron microscope were used in microstructural analysis. Hardness measurements were performed using Brinell hardness test with 31.5 and 2.5 mm ball diameter. The experimental results were discussed in this section. The MW sample code shown in the table 3 represents microwave sintering. The numbers 0, 5, 10 next to the MW code indicate the percentage by weight boron carbide particle ratio. Density values corresponding to produced and sintered samples are as in the table 4. The green density of samples decreased with increasing percentage by weight boron carbide due to the increase in porosity at the particle matrix interface. Compared to the green density values of all samples had decreased with the sintering process. The highest density values in sintered samples were obtained in 60 minutes sintering time. However, there is no fascinating difference between densities of the samples obtained sintering without holding time and sintering for 60 minutes. Figure 1 represents the SEM micrograph of the sample MW0 sintered at 555 degrees without holding time, and the EDS results shown in the table 5 were marked in the figure as point 1 to 4. Point 1, light gray particles. It contains 94% by weight silicon in EDS results. These are primary silicon particles. Point 2, the region containing light gray particles is master alloy. Point 3, dark gray region, elemental aluminum. And point 4, fine bright phases, copper secondary phases, copper and magnesium rich secondary phases, EDS results in the table 5. Figure 2 represents the microstructure map of the MW0 sample sintered at 555 degrees without holding time. The map shows that the primary silicon particles, blue ones, emerge in the original master alloy grains. Copper and magnesium-rich second phases had a homogeneous distribution in the master alloy and elemental aluminum regions. The SEM micrograph of the MW5 without holding time sample is shown in the figure 3. Master alloy pure aluminum region and boron carbide particles are summarized in the micrographs. The primary silicon particles have grown from the master alloy powder. micrograph of Alumix 231 samples sintered at 555 degrees are given in figure 4. When the micrographs are examined in parallel with the density measurements results, it was observed that the pores shrink and decrease with 60 minutes sintering. This change in pore size and amount with increasing sintering time can be explained by the grain join and growth that occurs with the effective transport mechanism in sintering. However, there is still an intense porosity and regional enlargement of pores in the microstructure. In addition, the bonding problems between the grains are seen in figure 5. There wasn't a good diffusion event and sufficient cohesion between the grains couldn't be achieved. Therefore, a long sintering time of 60 minutes didn't show the expected improvements in microstructure and density compared to without holding sample. And wettability of boron carbide particles and its bonding ability with matrix material are difficult. So, with the effect of sintering process, boron carbide particles push towards grain boundary.
Hello, hello. Kelly ma'am joined.
The highest hardness value was determined in the sample coded MW0, which was without holding time. There was no significant increase in hardness in the sample MW0 and MW10 at 60 minutes sintering time. Although there is no significant change in density, the decrease in hardness caused by the increasing boron carbide addition can be explained by the pushing of boron carbide particles into the pores and the grain coarsening during sintering. The decrease in hardness was observed with increasing sintering time in samples, grain coarsening with increasing sintering. Can I continue?
Please go on. Please go on.
Thanks. The decrease in hardness was observed with increasing sintering time in samples, grain coarsening with increasing sintering time, and inadequate bonding between grains may be the reason for this decrease in hardness. Conclusions were achieved in this study. Boron carbide particle reinforced Eka-Alumix 231 aluminum composites were produced through the cold press microwave sintering technique. Sintering process was carried out at without holding time and 4 different times. The green density of the samples decreased with increasing percentage by weight boron carbide. Compared to the green density values of all samples had decreasing with the sintering process. The highest density values in sintered samples were obtained in 60 minutes sintering time. However, these changes observed in sample densities were limited to small values. Different regions were identified in the microstructure of the Alumix 231 alloy, elemental aluminum matrix, master alloy, primary silicon particles, copper and magnesium-rich secondary phases. The primary silicon particles emerged in the original master alloy grains. The copper and magnesium-rich second phases had a homogeneous distribution in the master alloy and elemental aluminum regions. The highest hardness value was determined on the sample that didn't contain boron carbide and without holding time at the sintering temperature. sample hardness was observed to decrease with increasing boron carbide particle ratio. It was determined that boron carbide particles clustered in the pores. The samples were produced without holding time at 555 degrees, gave optimum values in terms of density and hardness. Thank GAZİ University for the financial support of this research work, and thanks for listening.
Thank you so much, dear Seher İrem. Is there any question to ask to Seher? Dear audience, do you have a question for these presentations? Okay, thank you so much. Very fruitful presentation.
You're welcome. Thank you.
Okay, see you there. Okay, then shall we start the next presentations? The investigation of effect of carbon and titanium additions on the mechanical, thermal, and microstructural properties of high alumina refractories. The title of the presentation will be presented by Irmak Su Öktem from 9 Eylül University, right? Is she here? No? Okay. Shall we pass to the presentation? And the third one, the presentation's title is Present Studies and Future Prospects of the Powder Metallurgy, Root Manufacturing High Pressure Turbine Discs. Osman Dur, are you here? No? Okay. There is no recorded presentation, then we will have to pass to another presentation. Ahmet Yönetken, are you here? No. Okay. Now, modeling. Do you have any presentation, Ahmet? I think there is no answer. Okay. I will check I think there is a uploaded video for this topic. I am not sure. There are two different presentation given by Ahmet Yönetken. Then I will check effects of sintering time on density. Effects of sintering, yeah. I think there is no, okay. Then Mübaşir Mansur here. Modeling and construction of economical laboratory scale graphite furnace capable of reaching 2500 centigrade in vacuum and inert atmospheres. Is there any guy to make a presentation? Let me check my downloaded video. Maybe he sent. Yes. There is a video, and then I need to, I think, share my screen. Okay. Okay. Can you see my screen now? Hello there. Can you see my screen? Ah, Mr. Mansur, try to attend to meeting room. Okay.
Yes, sir.
Yes, Mr. Mansur, welcome to, yes, that's
Thank you.
time
I'm
to.
sorry, we got a little bit delayed. The first part of our presentation, initial video presentation, which was recorded.
Okay, you will do by yourself, right?
If possible, we would like to do the
I
yes.
can't hear you well. Sorry. Okay, and then stop the video, and then I will let you share your screen, right? Okay.
Okay, sir.
Okay, I'm turn it off now. Okay. Sorry about that.
Yes, sir.
Okay, stop sharing now. Now you can share your page.
Thank you for giving the presentation link. I will just do this there. Thank you so much.
You're welcome. Okay.
Şu anda yapacak bir şey yok. Diğer şubelerden alacağız. Yani bu şube doluysa onu bir şey yapamam ben. Yani şu anda müdahale edemiyoruz zaten. Yani ekle bırak zamanı düzeltmeye çalışırız. Şu anda al başka şubeden. Yani ekle bırak. Her halükarda çalışıyor mu?
It's an honor to be presenting at the International Conference on Advanced Material Science and Engineering. Just like any other researcher in the field of technical ceramics and powder metallurgy, we love sintering, and so the temptation for climbing to ultra-high temperatures is just in our blood.
Ever since we started our sintering experiments, there was a single problem which kept limiting us in terms of the capacity to fulfill our sintering dreams. And that was the temperature limit of approximately 1,700 degrees Celsius due to the type of furnaces usually available in most labs. And it was not having the right equipment for reaching to temperatures over 2,000 Celsius. It was also interesting to see that a few of our colleagues who had access to ultra-high temperature furnaces had another problem. And that was the fear of doing experiments which could potentially damage the hot zone components, simply because these equipment are just a little bit too expensive. And for that reason, experiments done with such furnaces in most labs are too scientifically conservative, and the equipment are not used at all if there is a chance of a corrosive atmosphere evolution, as is the case in many liquid-phase sintering experiments.
We really wanted to see the magical temperatures of 2,000 degrees Celsius and above on our PID. So we started requesting quotations from a few companies who specialize in such systems. And to say the least, the prices were just too much for the budget that we had for sintering. We found with the idea of building our own furnace back in 2012. And after experimental trials, which mostly proceeded as a hobby, we now have a magnificent furnace up and running since 2015, which is capable of reaching 2,500 degrees Celsius with a hot zone cost of just $100 US. It has also become one of our best lab partners, proven to be quite reliable and a great tool for research on sintering of material which require temperatures in excess of 2,000 Celsius.
We have had so much fun with it that we thought there are surely many other researchers like us who may be interested in bringing together a furnace using equipment which most labs have laying around here and there in order to move forward with a furnace design which is too inexpensive to worry about its longevity, even if the experiments are rather damaging to the hot zone components. The immense possibilities that metallurgy and material science offer must be explored, and this necessity requires the ability to do experiments without the fear of an experiment cost.
When it comes to material selection for the hot zone, there are only a few options available which can fulfill the requirements we have discussed, both in terms of cost and material properties. Therefore, we proceeded with graphite due to its impressively high mechanical strength at high temperatures, low vapor pressure, ability to withstand temperatures up to 3,000 degrees Celsius, ease of availability, low cost, and rather simple machinability. There are very interesting graphite hot zone designs either published in academic literature or patented, some of which are widely used industrially. However, upon reviewing them in detail, we found that there are only a limited number of hot zone designs available that meet the requirements of a compact lab-scale graphite furnace for research and development purposes.
It is noteworthy that the majority of available designs require utilization of step-down transformers with ampere ratings of over 1,000 amps, thus increasing the primary cost of the furnace as well as the cost associated with replacing and repairing of the hot zone due to the geometrical setup of the graphite heating elements used and in the available designs.
An additional problem with graphite furnaces is the difficulty in quenching operations, which tends to be solved through rather operationally inconvenient procedures, such as high inert gas purging as in the case of the silica fiber drawing furnaces, making it rather challenging to quench a sample in vacuum. So with these points in mind, we proceeded with the following design criteria for the furnace.
The ability to reach 2,500 degrees Celsius in just minutes.
Capacity to sustain the mentioned temperature for several hundred hours if necessary. The ability to cool down the furnace at very high rates without using any fluids for quenching purposes.
And most importantly, maintaining the cost of the main hot zone as low as possible.
We decided that the total current utilized should be less than 200 amperes, and it must be operational on single-phase alternating current, with the intention of minimizing the cost of the step-down transformer and other electrical components necessary for the system. So we tried a series of different designs which were simulated by finite element analysis, and it was concluded that the optimized geometrical design shown here is particularly interesting for a number of reasons, such as the ability to provide a higher total power dissipation by the heating element in comparison to a cylindrical or polygonal hot zone of the same volume, considering a constant surface loading value on both cases, which facilitates approaching higher temperatures and also extending the longevity of the heating element.
Moreover, every cubic centimeter of high-purity graphite which has been sintered at elevated temperatures using hot hydrostatic press technology is very precious. So it is only logical to minimize the consumed graphite during machining of the geometry required. Therefore, in the proposed design, it is possible to simply machine slabs of graphite and to connect them using nuts and bolts made from the same grade of graphite, minimizing the wastage during the manufacturing process. It is also noteworthy that a similar volume of hot zone constructed in the conventional cylindrical or polygonal design consumes a significantly greater amount of raw material.
Our thermoelectrical simulations on various graphite grades have shown that it is possible to achieve a temperature of 2,500 degrees Celsius with an approximate power of just 2,000 watts for a usable hot zone volume of approximately 200 cubic centimeters.
Furthermore, the temperature variations within the central 60 cubic centimeter of the hot zone does not exceed 0.5% of the maximum furnace temperature. The mentioned values have been repeatedly confirmed experimentally.
The entire system works on single-phase alternating current, with the hot zone placed inside an ordinary vacuum chamber with two water-cooled electrical feed-throughs connected to a stainless steel chamber. And the entire system is practically consuming a power equivalent to 3 toasters. Another beauty of this design is that due to its size, the water cooling system has the capacity to cool it down very effectively if the power is disconnected. And we have seen an average cooling rate of approximately 300 Celsius per minute, from 2,500 to 1,000 Celsius.
On a different note, one should consider the thermodynamics of a system in which any sintering or heat treatment is to be conducted. It must be very clearly analyzed prior to any experimental work, as the furnace design in itself can have significant impact on the chemical equilibria which emerges, and also possesses the capacity to alter the phase equilibrium in solid state.
Therefore, we have done thermochemical simulations of the natural equilibrium of gases in the furnace, in absence of any forced gas flow, because even under such conditions, the thermochemical equilibrium as a result of Baudouin reaction can quickly become dominant in a graphite furnace, either in vacuum or inert atmospheres. The molar fraction of gases which emerge under 1 atmosphere total pressure are shown here. And it should also be noted that carbon monoxide's partial pressure cannot be ignored, regardless of the process in question. It should also be considered that the equilibrium partial pressure of oxygen in such a system is pressure dependent. Therefore, the choice of vacuum level or positive atmosphere's total pressure should be taken into account prior to experimentation with such a system. Special attention should be given to furnace atmospheres as a result of residual gases during a sintering or heat treatment operation, since this factor can have a very significant influence on microstructural evolution and defect chemistry of the material being researched.
So to conclude, every one of us researching in the field of ultra-high temperature materials, especially on refractory metals and their carbides, nitrides, or borides, can build a graphite furnace capable of reaching temperatures up to 2,500 degrees Celsius by bringing together the equipment usually available in most labs and a hot zone of just $100 with the service life of several hundred hours, paving the way for lots and lots of high temperature experiments.
With the only limit being our creativity. We are extremely grateful to our dear professors who have been a beacon of hope and inspiration, especially Professor Zohal Er at Physics Department, Professor Mustafa Urgen, and Professor Servet Timur at Metallurgical and Materials Engineering Department of Istanbul Technical University.
Thank you once again.
Thank you for giving us your time. We will be looking forward to any comments or questions you may have.
Yes, sir. Thank you very much for listening to us.
Yes, we are at your service.
We once again apologize for the initial delay. We were expecting our presentation to be at 4 o'clock, so I think we entered the session a bit in delay.
Apologies.
We can't hear you, sir.
Yes, you're on mute, apparently.
We can't hear you. It says you're on mute.
Okay, now you can hear.
Perfect.
Welcome to see you.
Thank you.
Very nice to see you. Okay, some presentation was missing. Then we will have to pass them. Then
I see.
because of that, your time.
Thank you so much.
We'll be more than happy to answer any questions that may be available. This was actually a very fun project for us.
Yes.
So we thought to share it and maybe inspire a few more people who might be interested in doing something similar, so that they can do perhaps a similar sort of hot zone in their labs and get some high temperature experiments going on.
The potential of the researchers are extremely infinite, and we hope to inspire perhaps our dear colleagues and friends, and looking forward to any questions you may have.
I'm not sure there is another audience can ask a questions. I am not sure. Is there any questions to dear team?
Thank you.
You're welcome. Dear guys, are you there? Do you have a question? I think there is no question for that.
If there is no question, please.
Sorry. You can make any design for furnaces or
It can be. I mean, from what we have had throughout this project was something quite interesting. Is we realized that generally the type of graphite furnaces, especially not just graphite, even the tungsten hot zones, or the kind of furnaces which require temperatures over 1700 Celsius, usually require the type of hot zones which are too expensive. So because of that cost, there are many labs who cannot either afford it, or if they do afford it, they usually, don't touch it. But if something breaks, then it's a huge cost. So what we thought about, maybe do something very similar to those, but do it a miniature design. So because the samples that we use in academia, they're very small anyway.
Yes, I wanted to ask. Yes, the same thing actually. Yeah, sorry about that. Interrupt your speech. Minimum dimensions. Could you give a
Yes. The internal
example for this? A minimum. Yeah.
It has about 60 cubic centimeters.
Really? Okay.
Yes. So the potential 60 cubic centimeter gives us very good thermal homogeneity. But the entire hot zone is actually 200 cubic centimeters. So it's not very, very small. It's actually larger than most of these SPS technology hot zones. So it's actually quite large. But from the perspective of the hot zones, which are usually available by these large companies
and used industrially,
those are huge.
Yes. According to dimensions, also price is changing, right? Linearly.
Exactly. We realized that actually the main hot zone can be constructed for at most $100, at most. And then it was even more interesting that the rest of the material, we don't even have to manufacture them. I mean, any lab that I have seen in ITU, there is a very good vacuum pump available, there is a vacuum chamber available, and there are many interested students available. So the rest is just automatically going to come in. So no need to pay huge sums of money for buying such ultra high temperature furnaces. All we need is the main hot zone, and then connect it to the any vacuum chamber that we may have. Something that I just want to underline, throughout the experiments that we have had, we have seen the importance of residual gases in sintering experiments to be immense. Especially at these ultra high temperatures. So for example, there have been cases where we have done a particular experiment, a particular sintering experiment, or maybe we were doing some diffusion experiment, and we were able to realize that the non-stoichiometry which arises in the system can have a very significant influence on the possibilities.
Yes, important issue. Yeah.
Exactly. So for that reason, my sincerest advice to any of our friends who are listening and who are doing research on any kind of material in any kind of a furnace, please check the thermodynamics of the system very carefully.
Yes.
Because we have this understanding that we heated up the system to, let's say, 2000 Celsius. We were in vacuum. So that's all that we write in many of the papers. But that's not all. The kind of vacuum, the kind of system, the kind of vacuum pumps,
all the variables have to be mentioned and have to be measured.
Yes, if possible. I mean, I understand that it's quite difficult to measure these residual gases very accurately, especially in these types of graphite furnaces, which usually are not very high vacuum. So we can't usually use a residual gas sensor. But what we can do is at least model the thermodynamics of the system using simulations like fact-based software or any calcified method. Using those methods, we can at least get an idea about the kind of non-stoichiometry that may arise. So, for example, there are some papers which indicate differences which may be 5,000 times when it comes to measuring diffusion coefficient. So, for example, especially in oxide. So, if someone is working with oxide, and they're sintering them at these ultra high temperature furnaces, they may be doing the same thing, but they may be getting very different results.
Definitely.
From what we have experienced with this miniature design of ours, was that if we change those residual gases, even a little bit, we can see a wide
design again, redesign again, maybe.
Exactly. And this was actually a huge benefit of designing the furnace ourselves, because we were able to manipulate the design very easily. So if it was a ready furnace from a particular company, then it would be best here to cut any part of it, because it would be a guarantee and it would be costly and so on and so forth. So having this simple design allows us to do lots of modifications.
And there's so much more flexibility flexibility, so much more curiosity. It gave us so much more power, actually. Yes, definitely.
And we were also, nowadays, we're working on the addition of pressure into the system. So it's actually quite simple to use this hot zone in a hydraulic press. So just add a hydraulic press, put the same thing, exactly everything else is the same vacuum chamber, everything. You may have noticed in our some of our pictures that the vacuum chamber has two flanges, one on top and one at the bottom. That's actually designed for a possibility of adding a press over there. So if we do that as well, then we might be able to do pulse DC type, SPS type experiments with the same design, and also do hot press type design. So it gives us a lot of flexibility. What I highly recommend to our dear friends is don't necessarily try to buy these things. Preferably make them. It's a lot more fun.
Exactly.
Very fruitful information for us. I didn't know exactly more informations for furniture. Actually, it was great for me. And then, if my colleagues needs this kind of special design furnace, I will let them know.
Absolutely.
Yes, contact.
For anyone working in academia, it will be a great honor for us. We're working. This project was advised by Professor Zuhal Er in the physics department of some technical university, and also we were very closely working with Professor Mustafa Urgan and Professor Servet Timur. They are very dear professors of ours, and it was hugely inspired by them in every step of the way. Their guidance was extremely crucial. So. We are more than happy to share the design, to share the blueprint, anything that we can do to spread the knowledge and also spread the word that build it out. It was so fun that we thought, well, it can have a great potential in academia, especially for powder metallurgy and for people working in sintering technologies. So anyone who does sintering, it's almost impossible to find a nice furnace which can go to 2,000, 2,500 degrees Celsius. It's very rare. And people who have it are very reluctant to allow using it for very specific kinds of designs, for a very specific experiments. So it's good to do it. We are more than happy to be of your service anytime.
Thank you again for your good presentations, very fruitful presentations and positive approaching from you.
Thank you.
You are great. Thank you very much.
Thank you.
Okay.
Thank you once again.
Okay. The next presentation is right now. I hope I'm making right pronunciation. Surya Narayana, right? Keynote speaker. We will get 4 different presentations from. Is he here? Could you hear me? No? Okay. Another keynote speaker, important speaker here, Mehmet Türker, right? I don't think so. He is here, I think. Yes. And then İsmail Er Yılmaz here? No. Harun Kahya. And then is there another presentation to make?
Gökhan Hocam, I think there is a connection problem because of I faced this problem. Maybe people will come, but there is a connection problem.
Really?
Yeah.
How to solve it? Do you have any idea?
I don't know. I don't know. It is solved, but I don't know. Because link connection asked me what is your password. So I don't need to password, I know, but there is one problem about the connection joining the meeting. Maybe they face to like this problem, I don't know. But By the way, I would like to say thank you for the Mansour's family. They are my hearts. So
Really?
yes, I am proud of them. So every time I will be honored to collaboration with you and them. Uh, They are perfect. So I'm proud of them.
You're very kind.
You're very kind.
Thank you.
You have always been an inspiration for us. Thank you very much. Thank you for everything.
Thank you.
It's always an honor
My
and a
pleasure.
privilege
It's my
to share
pleasure.
with you. Thank you.
Okay, very nice. And then, is there any guy you're willing to make a presentation? I'm not sure. I can't see any people easily from here. Maybe some guys waiting for to make a presentation. Maybe. I can't see any people. Shall we wait for some guys? It was very fast section hall because of the some guys couldn't attend the room, as I understand. Dear Professor Zuhal explained the situation. We can't hear you, Professor Zuhal.
My
Now.
opinion, they faced a similar problem because I tried to YouTube channel and most of time I changed my browser, but I didn't solve. Immediately they solved. It solved. I am here.
Shall we finalize? What's your suggestion?
Maybe they can they can pray. I don't know because it solved immediately, but I didn't understand. Maybe Adem Bey can manage, can control because I wrote to Adem, Dr. Adem, then I accepted to this meeting.
Okay, but we can see him and then maybe we can ask a help
Yeah.
on this. Sorry about that. Sorry for waiting. Now I am downloading some videos. I think there is some presentation. I am not sure. I will check them. Re-downloading again. Sorry, there is no new video. I download this.
No problem.
Mhm. We will have to wait, I think, at least for me, for section chair. I need to wait the other speakers.
Maybe we can offer the change of the browser to the participant. Maybe I can solve, but I am not sure. But most of times I try to Firefox, Google, Chrome, and everything. Then I solve.
Mhm. Shall we make a short break for this? Maybe some speaker can attend
Sure.
after solving this problem.
Of course. So
So recorded, Mr. Mansur. Shall we need
Thank you
to
very
turn
much,
it
sir.
to... Sorry?
Thank you very much.
Thank you.
We're
Thank you
very
very much.
enjoying
We will give a short break.
That would be great.
Okay.
Thank you.
See you.
see
See you
you.
soon.
Bye-bye.
Bye-bye.
Bye-bye.